Good evening and welcome everyone to this talk. I am Chinmay Soman, founding engineer in StarTree. I also lead the product org here, and definitely amazing to be back at my previous employer. So thank you for having me. Today I'll be talking about what's the secret sauce behind Apache Pinot. What makes it so fast? So we'll go through the architectural decisions that led us to this place. But before, why do we care? We all know, for OLTP databases, speed, throughput, and latency that's very important. But why does it matter for OLAP use cases, right? Ujjwala sort of touched upon this already, but in case you're still not convinced, here's some more examples. This is the classic one from LinkedIn. And so LinkedIn provides a lot of analytics and insights to their users. So things like talent insights, the classic who viewed my profile, and then also the content relevance for your newsfeed. So they basically analyze user behavior and then ensure that you're seeing the latest, most relevant content on your feed. And most of these applications behind the scenes are running OLAP queries, something like this. Right? So it has some aggregations, filter, group by, order by, maybe even joins. So the query themselves are not that complicated, as you can imagine. But the scale of things is what makes it very challenging. Right? So LinkedIn has 930 million plus users from my today's Google search. Has obviously to support these user-facing insights. Any active member on LinkedIn, when they are browsing through the site, they're firing these queries on the backend. So we're talking about tens of thousands of QPS, and the main part here is the latency SLA, which it has to be less than 100 milliseconds for P99. This is another great example from Stripe. I'm actually stealing this slide right from Lakshmi, who's sitting right here. So thank you for that. But Stripe has a real-time platform which is used for building all kinds of dashboards that they expose to their merchant, like the merchant partners, internal developers, and so on. Also used for other things, as Lakshmi mentioned, billing analytics, developer analytics, and so on. And again, the scale of things and the latency SLA is quite stringent, right? So talking about 20,000 plus QPS, and then even stringent SLA here, in this case, less than 50 millisecond P99. And of course, I think Ujjwal already showed this, but here's the Uber Eats example where this dashboard is shown to, again, my Google search says it's 900,000 restaurant partners as of today. Every time they log into this dashboard, they get a view of the order status, missed orders, and financial stats, and so on. So you're talking about lots of QPS, and again, the latency here has to be sub-second and in a predictable manner. So all these use cases and many more is being powered by Apache Pinot today. For those who are new to Pinot, it's a distributed OLAP database coming out of LinkedIn that can ingest data from all these different data sources you see on the left, like Kafka, S3, GCS, and then make it available for serving and power a wide range of use cases, as we saw before. The last few years, we have seen a massive adoption amongst different companies across the globe, and in different segments, right? So you have prominent names like Walmart, Target, 7-Eleven on the retail sector, Citibank, Stripe, VPay, and so on, and the financial services industry. Food and logistics is actually where I think Pinot is a segment winner. Every major company in this segment across the globe has actually adopted Pinot, which is monumental, and so on. So it's quite popular across all these segments. Also quite a vibrant community, 3,900 plus Slack members and counting, and lots of Docker downloads, which is great. All right, so for the rest of the talk, the structure is the following. Right? We'll go through the high-level architecture of Pinot just to understand the basics of query processing and what are we trying to even optimize. And then look at optimizations applied to different layers in the stack to get this speed and the scale that Pinot can support. All right, so as I mentioned, Pinot is a database, right? The table in Pinot is a logical concept composed of what we call as these Pinot segments. Right? So Pinot segment is a subset of your data. If you sort of peek into it, it's actually the data organized in a columnar fashion, along with any of the indexes that you've specified on your table. So in a Pinot cluster, all these segments are sprayed across the available Pinot servers. So Pinot server is a component that locally manages and processes the segments and then generates a result. We also have the Pinot controller. That's the brain of the whole cluster. Takes care of membership, coordination, segment assignment, and so on. And finally, the Pinot broker. So that's responsible for query processing. Every time it gets a query, it does a scatter gather to generate a result. What that means is it will identify which servers do I need to send this query to, right? Those servers in turn will locally process the query, generate an intermediate response, and then broker will collect all these responses, do a final aggregation, and then return the result. So as you can see, it's a good scale-out design. So if you want to handle more data, more QPS, you just keep adding more components, and then it horizontally scales quite well. One thing to note is without any optimizations, the broker will try to process every single segment that's available in that table. And this is key to understand, right? So that means in this case, it's going to, for any query, it's going to try to process all 12 segments here. So the whole purpose of optimization is to minimize the work done per query, right? What that means is minimize the number of segments that we need to process, and also minimize the number of servers that we need to process to answer a given query. And then, as you can expect, these optimizations are applied at different levels in the cluster. So there's some applied at the broker layer, there's some optimizations at the server layer, and then finally also the biggest optimization is actually at the segment level. So in the next few slides, we'll go through each one of these optimization in detail, starting with broker, right? So as I mentioned, broker will try to process everything without any hints or any optimization applied. So there are a few things that we can do to simplify this at the broker layer. One is time-based pruning, right? So let's assume the broker gets a query like this. Select some aggregation for a given time range, right? So Pinot table, there's a time column that you can define in your schema. And for that time column, I want to generate an aggregation for a specific time range, right? Naturally, all segments here don't matter, right? We want to select only those segments that fall in the time range. So in this case, the broker can look at the segment metadata, which includes things like start time and end time of each segment, right? And just by looking at this, it can filter out most of the segments that fall outside of this range and only focus on the ones that are relevant. So for example, let's say only 1 and 3 are relevant here. So broker can now, without looking at the data, it can only send the query to server 1. So from a fan out of 4, almost like 75% reduction in the work that we are doing to answer this query.
So are segments updated in place?
The question was, are segments updated in place? Well, the segments are immutable, right? So once you generate a segment, the indexes and the data are locked in. There is a way to update it in the form of upserts. So if you have a primary key on your table, you can mutate that data, but that's handled in a different manner. So the segment themselves are immutable, but we can still provide this functionality. But in this case, the segment metadata is basically locked in, if that's what you were getting at. So that piece is static. Another thing we could do is partition pruning, right? This works when your data can be partitioned on a certain column. Right? So for example, let's assume this is a query you get, select count star, where user ID is whatever. And the assumption here is you have a lot of queries that are trying to filter on user ID column. In this case, you could partition your data on user ID and specify that in the Pinot table config. So Pinot knows the data is partitioned on user ID. In this case, again, when a query like this comes in, it can look at the segment metadata, which includes the partition information, and then filter out most of the partitions that don't have whatever partition 1, 2, 3, 4 maps to. It can filter that out, and again, focus on only a few segments instead of all the segments. A third thing that you can do at the broker layer is to reduce the fan out. Right, so the fan out is basically how many servers you're trying to reach for answering a query. So another concept that Pinot has is called as replica groups. So this is not really a broker concept. This is a way to sort of assign segments amongst the available servers. So replica group is basically a collection of servers that contains a full copy of the segments in the table. So you could take, you can define a replication factor of 2. One group contains all the segments, the other group contains all the replicas. So this is the same segment is in both the groups. So what this allows the broker to do is to query any one of these replica groups. So suddenly from a fan out of 4, now you only need a fan out of 2. You reduce it by half, basically. So obviously this is good for the latency, but also improves throughput, and which is important for all the use cases we saw before.
So reducing fan out also has impact on the scalability, right? We tend to limit scalability also by reducing fan out.
Yeah, good question. The question was, we're reducing the fan out, but we're also reducing the question is, does this reduce scalability or not? Well, you can always increase the number of servers within a replica group, right? So that still remains. All you're doing is, instead of spraying segments randomly across the servers, you're saying limit it to like these servers, but you can still have 4 or 8 or 16 servers within a replica group.
This will also increase the fan out, right?
Yes, so it's a fine balance between obviously data scalability and replica group, but then you can apply the other optimizations which will help. All right, so with some of these optimizations, we have reduced from like 12 segments to, let's assume, this is a hypothetical example, but we basically reduce the number of segments by doing stuff only at the broker layer. So we haven't touched the data so far. So now let's look at what happens in a server. Right? So in some cases, you can only prune the segments so much at the broker layer. So we can do further optimization at the Pinot server. Right? So let's assume you're getting a query like this on a different column. You're filtering on player ID, for which you don't have the previous optimizations. In this case, we can define a Bloom filter on this particular column. Right? So each of these servers will have a Bloom filter on player ID. And when it gets the query, it can use the Bloom filter to again filter out segments that don't contain that particular value of player ID. Right? So in this case, it will, without looking at the data, we still haven't touched the data so far, we can eliminate segment 3 and just focus on segment 1. Right? So this enhances, again, it further cuts down the number of segments you need to process for answering the query. All right, so at this point, after this, we now need to do the segment processing. We can't obviously avoid the hard work. So let's see what happens within a segment. Right? As I mentioned before, segment is a subset of your data. So assume these are some subset of your input rows. When you create a segment from these rows, basically it takes the data and organizes it in a columnar fashion. Right? So in this example, all the values of country are stored together. Same thing for the browser and so on. This already is pretty optimal for OLAP queries. Right? So for example, if you want to do an aggregation and filter on some specific country, right? Instead of having to scan all the rows in a typical row store, you only need to look at one column, which is the country column. Right? So this reduces how much data you need to scan from the disk, how much data needs to be brought in memory, and obviously great for the query latency. Right? This improves latency and throughput indirectly. But the other thing you could do is add an index for that column, right? So in this case, we can add an index on country, right? So instead of scanning even like one column, we don't have to scan at all. We can just look up which document IDs or which rows have that particular value and do a quick aggregation. And Pinot, this is the best part of Pinot, right? It comes out of the box with a wide range of indexes, which can accelerate different kinds of use cases. So you have inverted index and sorted index, which works on numerical values, and you can do things like look up pretty fast. So if you're going to filter on some column with an equal to clause, these two indexes work great. If you have a range query, so if you have where hits is greater than 11, something like that, you can use a range index in that case. For semi-structured data, you could actually configure JSON index. So imagine one of your columns is actually just JSON data. You can configure JSON index on it and do JSON match queries, which will be much faster than defining like a UDF for JSON. Similarly, you could define a text index for if you have just a string column, you want to do text search on this. This could be prefix, suffix, or regex, whatever you want to do, right? The text index will accelerate those kind of queries. And then geo index is actually, thank you to Uber for contributing, but for any sort of geo data, you could use this index for accelerating point and polygon or distance kind of queries. So these were all these indexes accelerate the filtering phase of a query. So whenever you're doing a where clause, these indexes will help in minimizing the number of records you need to scan for processing the query. The other thing available in Pinot are things to accelerate the aggregation function themselves. Right? So if you're trying to do approximate functions, there's theta sketches, HLL, and tdigest, which is available today for fast aggregation. And then last but not the least is our favorite StarTree index, which does both things. It can actually help in the filtering part as well as aggregation part. The way it works is for a given set of dimensions, it will pre-compute some aggregation function across all kinds of combination of those dimensions. So whenever a query comes in, it can very quickly look up an aggregation, the pre-computed value without even having to do much scans. The why indexes matter in these kind of databases, right? So when we compare this versus other databases that don't have indexes, this chart will explain the key difference, right? When your data size is small, right? If you're a few nodes, most databases will give you great latency and throughput. But as you keep growing, as you keep organically adding more data, adding more QPS or concurrency, this is the pattern we see, right? Without indexes, you're bound by how much data you have to scan for a given query. That grows linearly with the amount of data. With Pinot, on the other hand, the goal is to sort of keep this curve as flat as possible, right? So even if the data grows, workload grows, we minimize the number of things that we need to process using indexes and get predictable latency even with increased growth. These are some of the benchmarks we've done internally on the different with and without the index, right? So as you can see in some of these cases, there's many orders of magnitude difference, especially visible in StarTree index. This is one of the blogs we posted from StarTree side, where this is one of a real world use case where the latency went down from like 592 millisecond P99 to 25 millisecond. Not only that also helps you get a huge increase in throughput. The max throughput before was about 28. I was like 2 orders of magnitude higher with StarTree index.
What's the cost of an index? Like for the same data, we can have multiple indexes, and now when we are ingesting data into that table, we'll have to update all these indexes, right?
So the question is, what is the cost of an index, and do we need to update an index as new data is ingested? No. So The cost of an index is there, obviously. Like every time you add a new index, there is more storage footprint, there's more memory that's being utilized. But when a segment is committed, the indexes are basically final in that, right? You can regenerate the segment, but once it's generated, you don't have to touch it again. Obviously, this for a new consuming segment, this matters. Some of the indexes are only generated when it's committed, not during real-time ingestion. Yeah.
I'm just curious, is it dynamic indexing or it has some frequency?
Sorry, can
How
you?
does the indexing happen?
Question is how?
Dynamic, real-time?
Yeah. So question was, how does indexing happen? So let's say you define an inverted index, right? For real-time ingestion, like it will be as your data is being ingested, it will keep updating the dictionary and the index in memory. And when you commit it, you flush the columnar data along with the indexes on disk, and after that it doesn't change. So yes, the indexes are real-time. So for any fresh data, it will actually leverage the indexes, and for at least for inverted index. All right. So through this, through the slides, we saw that Pinot is indeed powering many mission critical use cases across different companies. And it was designed from the ground up for like supporting high QPS, low latency in a predictable manner. So it is able to achieve the strict SLA across all these companies. It is an indexing powerhouse, so it can, it's a wide range of indexes available for accelerating different kinds of use cases. We're trying to minimize the work done per query. That's really the design principle across the board. And also it's a scale-out architecture. So after a certain point, you optimize as much as possible. You can always add more resources and horizontally scale your workload. And that's it. So Pinot is indeed fast.